Midas NFX Lecture 5, Transient Thermal Analysis. So this is a transient heat transfer problem. First of all, we can open the case and give it a name. And import the geometry. So we have finished with the step 1, drawing a 3D model and opening a case. The second step would be material. First of all, we load a material, isotopic material, aluminum alloy, 6061. This is a material generally used for computer heatsink. So this is loading of material, and then we can connect the material with the geometry. And this is the only geometry, the heatsink, and we give it the material 6061 aluminum alloy. So we have finished with the second step. For the third step, we'll mesh the geometry. And I'll select the geometry and take a default mesh size and perform meshing. So we can run the step 4. I'll heat the surface, the bottom surface. And since there's no heat power, so I'll use heat flux instead. So first of all, I'll choose the surface to be the entity, and I choose the bottom surface to heat. And it is about 28 watts heating, but I did not draw the CPU model, so I simply heat the surface. And it is 28 watts divided by 2500 millimeter square, so it is 0.0112. But in the steady state problem, I type 102 instead. So now I'll make it 112. It is actually 112. So this is a number where the total area has a heat power of 28 watt per second. So this is the heating of the bottom surface. And now we're going to define the constraints. The heating will be the loading, right? So we're going to define the constraint, which is the convection. And I'll choose surface also. And for the object, I will select all surfaces. And then deselect the bottom surface because it is the heating surface. So whatever the surface in contact with the fluid or the air must be chosen. So it is about 156 surfaces. And for ambient temperature, you can define it to be 20 or 25 degrees C according to the room temperature. And the convection coefficient, first of all, I will change it to meter so that the unit will be watt per meter square. It is SI unit. It will be 10 watt meter square. If it is in millimeter, the number will be 10 to the minus 5. So I'll go back to SI unit. It will be 10 watt meter square K. So this is the convection coefficient, and this is the ambient temperature. So I have finished with the step 4. Now with step 5, I can include a analysis type, but there's no transient heat transfer, so it is in other. So first of all, I'll give you the name, and then choose the transient heat transfer module. Now in transient heat transfer, there are two things that is different from steady state thermal problem. The first thing is the initial temperature. In the steady state analysis, since the time is infinity, so the initial temperature does not matter. But in transient analysis, the initial temperature will affect greatly the result. So the initial temperature is very important. But how much is the initial temperature? It may be 20 or 25 or 30 degrees C according to your room temperature. And also the time to be calculated. For example, the total time will be 1 hour, and then it will be divided into 120 steps. So these are the things that are different from the steady state thermal analysis. First of all, in transient thermal analysis, you need to define initial temperature, the temperature at time 0. And then there's a requirement that you need to give it a time to calculate. So I give it an hour. So I would like to know how much temperature is changed during the hour. So now we have defined the subcontrol, the setting of the transient thermal analysis. So we can go ahead and calculate the solution or perform the calculation. And since there are 120 steps to calculate, and it will take a little bit of time, so I will stop recording will be paused for now. So now the solution phase has come to an end. So first of all, I will look at the temperature distribution at the final step here, and I'll probe the temperature at the final step, which will be 125 or 126 degrees centigrade. So in the steady state, I got 126. So at an hour, it is almost a steady state condition. And now I'll extract the data where I'll choose a node here at the top surface, and I'll let it give me the temperature table for the entire process. So now I'll mark all the data and let it graph. It'll construct a graph. I'll choose the x-axis to be the number of steps and the y-axis to be the temperature. So this will be the result for the temperature at the top surface, the node point that I chosen. So you can see that the temperature rises from 20 degrees C, where it is room temperature, the initial temperature, and up to 126 degrees C. And at about 1000 seconds, the system reaches the steady state. So steady state thermal process signify that the time approaches infinity and the system approach a thermal equilibrium, and the temperature of the system does not change anymore. So the heating and heat dissipation are balanced. So we can see that how the temperature rise from room temperature to the target temperature of steady state temperature. So this is lecture 5, the transient thermal analysis of Midas NFX.